10 days ago, the newest images of 3I/Atlas appeared online and instantly sparked a wave of fascination and confusion. At first glance, it looked like a comet, but the strange plasma-like glow around it and the stream of gas flowing toward the sun instead of away from it didn't match anything we've ever seen in our solar system. Rumors and edited photos exploded across social media, burying the real discovery under layers of speculation. This video cuts through that noise and explains what the verified data actually reveals. Yet a larger question sits at the center of everything. 3I/Atlas is changing in ways no one predicted. So what exactly is it becoming next? Before we dig deeper, tell us in the comments, did you already know comets could behave this strangely, or is this blowing your mind as much as ours? And be honest, does any part of this make you a little nervous? 3I/Atlas entered our view on November 17th. Immediately, astronomers noticed something strange. Its speed didn't match any object normally found in our solar system. Very quickly, scientists realized that it must have originated in interstellar space, because its path didn't trace back to the distant Oort cloud, where most long-period comets are born. The Oort cloud is a vast shell of icy bodies surrounding the solar system, and comets typically come from there after being nudged by passing stars. But 3I/Atlas didn't follow that pattern. Its trajectory pointed back to a region far beyond the sun's gravitational reach, confirming its interstellar origin. That alone made the discovery feel almost unreal. Objects from outside our solar system rarely pass close enough for us to study them in real time. Then came the speed measurements. Quick question while we're here. Do you think this interstellar visitor just wandered in by chance? Or does this trajectory feel a little too perfect? Drop your theory in the comments. Serious answers and wild guesses equally welcome. And hey, if your comment accidentally predicts the future, we promise to act shocked later. When 3I/Atlas was first detected, it was already traveling at nearly 58 km/s, and that velocity increased rapidly as it moved toward the sun. Most comets accelerate as sunlight heats their frozen surfaces, but 3I/Atlas began this acceleration much earlier than expected. Near its closest approach, it hit almost 68 km/s, making it one of the fastest natural objects ever recorded inside the inner solar system. This extreme speed made early tracking difficult. Even tiny measurement errors created massive differences in predicted positions. Astronomers had to combine observations from multiple observatories just to lock down its true path. But as the data improved, one thing stood out. 3I/Atlas moved along a smooth, stable trajectory. No sudden jumps, no chaotic spinning, none of the unpredictable behavior sometimes seen in interstellar visitors. This stability allowed scientists to eliminate many early fears and focus instead on the physical traits that make this object so unusual. The shape of its orbit told another story. 3I/Atlas has likely spent millions of years drifting through deep space before finally falling under the sun's gravity. That long, silent journey means it has survived collisions, radiation, and unimaginable cold, adding even more weight to the mystery of its sudden arrival. Before we continue, tell us below, does this perfectly smooth trajectory make you more curious or more suspicious? We read every comment, even the ones that sound like they were written by 3I/Atlas itself. If you want to follow that next discovery, make sure to like and subscribe and stay with us. The story of 3I/Atlas is only beginning. The first images of 3I/Atlas triggered instant confusion. Only hours after its discovery, the object already looked unlike anything people expected to see. When astronomers captured the earliest frames, viewers noticed something bizarre. The bright coma surrounding the object appeared to lean toward the sun, not away from it. Normally, a comet's coma grows in the opposite direction of sunlight, but 3I/Atlas showed the reverse behavior in its very first photographs. The orientation was so strange that researchers double-checked their instruments, repeated their measurements, and compared their results with other observatories, just to make sure nothing had been misaligned. It wasn't a glitch. Multiple observers across different countries reported the same thing, a dense, forward-leaning coma pushing toward the sun. This suggested that 3I/Atlas was reacting to sunlight in a way that didn't match the typical physics of comets formed inside our solar system. Some astronomers proposed that the object might be shedding material unevenly, creating a temporary jet on one side that pulled the coma forward. Others suggested that the odd appearance might simply be a trick of geometry, a result of the angle between Earth, the Sun, and 3I/Atlas at the time of observation. Long exposure images only added more confusion. Light streaks, camera shake, and atmospheric distortion created artifacts that made the coma look stretched, twisted, or doubled. These visual glitches fueled online speculation as dramatic images spread faster than accurate ones. Soon, viewers were debating whether the object had multiple tails or none at all. Some photos showed a faint streak trailing behind the object. Others showed no tail whatsoever. But these inconsistencies didn't mean the object was changing rapidly. They simply reflected differences in equipment, exposure settings, and processing techniques among amateur astronomers. Many people unfamiliar with astrophotography trusted the most dramatic images, even when those images exaggerated or distorted key features. Meanwhile, professional astronomers had to remind the public that early comet images often look unstable because the object is still heating up as it approaches the inner solar system. As 3I/Atlas moved closer to the Sun, astronomers expected new jets of gas and dust to appear, slowly shaping a clearer, more recognizable tail. But the early confusion surrounding the object revealed something important. First impressions in astronomy can be misleading, especially when the target is evolving at high speed. And that raised a much bigger question. If the very first images looked this strange, what would happen once the object heated up and began releasing even more material? In the days that followed, it became clear that 3I/Atlas had entered a new phase. As sunlight reached its surface, the object began releasing gas rapidly. The coma grew brighter, expanding and becoming more active as the object moved deeper into the inner solar system. This behavior matches what happens to comets when they warm up. But 3I/Atlas reacted earlier and more intensely than anyone expected. Long exposure photographs revealed newly forming jets of gas blasting off the surface, pushing dust outward and creating the early structure of a tail. The tail looked uneven at first, almost chaotic. Strong solar heating collided with the object's natural rotation, making some regions warm faster than others. The result was a series of short, sudden bursts that appeared across multiple images. Each night, these jets gave astronomers new clues about how much energy the object was absorbing. Out in interstellar space, an object like 3I/Atlas receives almost no sunlight. But once inside our solar system, the jump in heat was dramatic. This surge altered its chemistry, releasing dust, gas, and ionized particles. Together, these components created a plasma-rich environment that became more obvious with every new photograph. Researchers also noticed that parts of the tail held large amounts of ionized material that glowed vividly under sunlight. This plasma interacted with the solar wind, shaping the direction of the tail and pushing it outward, while pockets of dust continued to thicken inside the coma. The result was an object that looked almost alive, constantly shifting and reshaping itself. As the jets strengthened, the tail stretched into a clearer, more stable line that even small telescopes could detect. Observers across multiple countries confirmed the same features night after night, proving that the changes came from the object itself, not from camera errors. The rapid transformation reminded astronomers just how quickly a newly heated comet-like body can evolve under intense solar influence. Each night brought new structures, and within days, 3I/Atlas became one of the most closely watched objects in the sky. This growth also sparked curiosity. Once even more images reached the internet, how would people interpret what they were seeing? That question didn't take long to answer. As the discovery spread, confusion surged online. Many users shared images without checking how they were captured. Some live streams showed a faint fuzzy object, exactly what astronomers expected at this early stage. But edited versions soon appeared, with artificially sharpened edges and exaggerated colors. These dramatic images looked mysterious and impressive, and many viewers assumed they were real. Others cropped images so tightly that they removed surrounding stars and exposure information, making the object appear more structured or engineered than it actually was. In several cases, people posted artwork based on early frames without labeling it. Once those stylized interpretations began circulating, they were quickly mistaken for real data. This sparked a chain reaction of misinterpretation across social media. Confusion intensified when another comet, K1 Atlas, began to fragment during the same week. Many users saw the name Atlas and assumed the breaking pieces belonged to 3I/Atlas. The timing made the misunderstanding spread even faster. K1 Atlas was undergoing a completely normal breakup caused by heat and structural weakness, a common fate for fragile comets. But viewers unfamiliar with comet naming systems assumed that the interstellar visitor was splitting apart as well. Dramatic headlines soon appeared, claiming that 3I/ATLAS had fractured into multiple pieces. Astronomers had to repeatedly clarify that the two objects were unrelated and located in entirely different parts of the sky. Still, corrections spread far more slowly than the early rumors. The mix of edited images, mislabeled artwork, and incorrect assumptions showed just how easily a real scientific discovery can be drowned out by online noise. The sudden explosion of public interest brought excitement, but also chaos, long before accurate details could be verified. While the conversation grew more tangled, scientists focused on collecting clearer data from professional instruments. This became increasingly important as new observations arrived from different angles across the solar system. And one set of observations, captured from the vantage point of Mars, would soon change everything. The release of this Martian data gave scientists a completely new perspective on 3I/Atlas and became one of the most important developments in the investigation. Soon after the object was first detected, the European Space Agency, the ExoMars Trace Gas Orbiter, was one of the first spacecraft to provide a second viewpoint on 3I/Atlas. Its cameras had been monitoring the region of space the object was passing through, capturing faint frames where the object appeared as nothing more than a tiny moving dot buried in background noise. The images weren't sharp, but their value wasn't in their visuals, it was in their geometry. Because the orbiter viewed 3I/Atlas from a completely different position than Earth, the new angle allowed researchers to refine the object's trajectory with far more precision. Once scientists combined the Mars data with Earth-based observations, the predicted path improved by nearly an order of magnitude. The updated calculations showed a smooth, stable course through the solar system, no sudden turns, no unexplained accelerations, and no force pulling it off its expected route. With this, many of the early rumors about intentional movement or hidden propulsion quickly faded. The Mars perspective also explained why Earth-based images had looked distorted in those first chaotic nights. The different viewing angles compressed or stretched parts of the tail depending on where the observer was located. At the same time, 3I/Atlas was still reacting violently to sudden heating. Its jets were unstable, spraying gas in shifting directions that sunlight highlighted unevenly. The Mars readings confirmed that most of these strange shapes were simply perspective tricks, not physical anomalies. The data also showed that 3I/Atlas experienced a small but steady non-gravitational push, exactly what scientists expect when gas escapes from a warming surface. Nothing in the numbers suggested anything artificial. For many researchers, these findings were a relief. They helped steer the conversation back toward science and away from speculation. As more data flowed in, one factor stood out, something many viewers had overlooked. The sun itself was shaping the appearance of 3I/ATLAS far more aggressively than anyone realized. During the first week after the discovery, an active sunspot region, AR4284, rotated across the solar disk and unleashed several bursts of energy. These flares released waves of charged particles that swept through the inner solar system, and any object in their path reacted immediately. Instead, exercising effectively means building a moment of self. As the particles struck 3I/Atlas, they altered the environment around it and shifted the shape of its developing tail. At the same time the jets were reacting to heat, the solar wind was bending and twisting them in new directions. In long exposure photographs, these faint distortions became exaggerated, making the tail appear thicker, bent, scattered, or even broken. None of this meant the object itself was unstable. It was simply being pushed, pulled, and reshaped by a constantly changing stream of solar particles. On the most active days of the sunspot cycle, the solar wind grew stronger, brightening parts of the tail and stretching others into sharp streaks of light as dust grains interacted with the charged environment. On quieter days, the glow faded or thinned. To viewers unfamiliar with solar physics, the changing shape looked mysterious, almost intentional. But when scientists compared the timing of each solar flare with the appearance of the tail recorded that same night, clear patterns emerged. The sun, not the object, was responsible for most of the dramatic variations. Still, the internet had its own ideas. As images spread, many people began to wonder whether 3I/Atlas carried properties that didn't align with natural objects. The constant changes in brightness, the early sun-facing coma, and the structured jets convinced some viewers that the object was controlled, reacting with intention rather than physics. Online discussions grew louder. Some pointed to patterns in the jets, claiming the symmetry suggested technology. Others focused on the plasma glow, arguing that its intensity hinted at an unknown power source. Researchers, meanwhile, remained grounded in the data. They saw no sign of propulsion, no sharp maneuvers, and no accelerations outside what gas release could explain. Rotating bodies often produce repeating jet patterns, perfectly natural behavior that can look engineered when captured in long exposures. Plasma brightness shifted with solar wind intensity, not with the object's motion. The unusual appearance came from three factors: its interstellar origin, its sudden exposure to strong sunlight, and a highly active sun. Unfamiliar didn't mean artificial. By the end of the week, attention turned toward the next phase of the journey. 3I/Atlas was now moving deeper into the inner solar system, and the changes became increasingly dramatic. Sunlight continued to heat the surface, intensifying the jets and pushing more dust and gas outward. The tail grew longer, brighter, and far more structured. This stream of interstellar material formed a trail that scientists hoped to study in the coming weeks. Lighter particles drifted wide, heavier ones stayed close to the main spine of the tail. Classic behavior for a natural body under heavy solar influence. Researchers also noted that the object was approaching the orbital plane where many planets travel, a region filled with ancient dust. Objects that pass through this area often leave material behind, material that can eventually create faint meteor streams years or decades later. It was too early to know whether 3I/Atlas would produce one, but the possibility added another layer of scientific interest. Meanwhile, the object was approaching its closest distance to Earth, not dangerous, but ideal for high-resolution imaging. Observatories worldwide prepared for the moment, and NASA announced that new, sharper images were coming soon. These upcoming frames would finally reveal what lay beneath the glowing coma, the true size and shape of the nucleus. If the core was small, its rapid activity would make sense. If it was large, it could explain the intense jets and early brightness. Either answer would reshape theories about the object's long interstellar journey. As this next chapter approached, one thing became clear. The first week of 3I/Atlas had already rewritten expectations. What began as a faint discovery quickly grew into a global conversation filled with speculation, science, confusion, and discovery. Each night revealed new jets, new structures, and new mysteries. The combined observations from Earth and Mars confirmed the object's stable path while highlighting its strong reaction to sunlight. And with NASA's high-resolution images just ahead, the early chapter of this story was coming to a close, opening the door to whatever the object would reveal next. If you want to follow that next discovery, make sure to subscribe and stay with us. The story of 3I/Atlas is only beginning.